Me suenan a música los cantos de tus aves, el ruido de los vientos que no mueven tus árboles. En el frondoso bosque el sol se multiplica y yo me hago más grande, embobada en belleza.
Throughout our history, different cultures have used geometry for decorative purposes, employing the practice of tessellation of surfaces to construct different mosaics. A tessellation is nothing more than filling a surface with a repeating geometric pattern. The Arabs were pioneers in this field and contributed remarkable results, taking this art form to a new level. However, it was not until 1891 when the Russian crystallographer Edgar Fedorov made an exhaustive study of the possible ways of tessellating a plane, enunciating the theorem that bears his name. Fedorov's theorem affirms the existence of only 17 possibilities, known in mathematics as the 17 crystallographic plane groups. The study of the different geometric characteristics constitutes the foundation of the symmetries on which crystallography is based. The concept of symmetry from the mathematical point of view is specified when studying the different movements in the plane, called isometries. There are 4 fundamental movements or isometries, which are the following. Translations. They move each point of the plane the same distance, determined by the translation vector. Rotations. We fix a point and rotate the object about itself a given angle. Reflections. Roughly speaking, it is the result of reflecting an object in a mirror. The straight line with respect to which it is reflected is called the axis of reflection or symmetry. Sliding reflections. By composing a reflection with a translation, we obtain this movement. To study a mosaic, it is necessary to identify the fundamental parallelogram, which fills the plane by repetition in 2 different directions, and they involve isometries. Fedorov classified the crystallographic groups according to the maximum order of rotation, understanding by order of rotation the number of times that a figure has to rotate a fixed angle around a point until it runs into itself. If this angle is 180 degrees, we will say that it has order 2. If it is 120 degrees, order 3, 90 degrees, order 4, and if it's 60, order 6, not to mention the possibility that there may not be any rotations. Based on this, the 17 crystallographic groups are as follows. No rotations, 4 groups of isometries. Order 2 rotations, 5 groups of isometries. Order 3 rotations, 3 groups of isometries. Order 4 rotations, 3 groups of isometries too. And finally, order 6 rotations, where we have 2 groups of isometries. As we can see, the notation consists of, at most, 4 symbols in a fixed order. The first symbol refers to the fundamental parallelogram. The second depends on the maximum order of rotation, with a 1 appearing if there is no rotation, a 2 if the rotation is of order 2, and so on. The third distinguishing mark will depend on whether the mosaic has symmetries. We will denote with an M when it is a reflection, with a G when the reflection is a sliding reflection, or with a 1 when it is neither of them. The last symbol's presence is dependent upon whether the aforementioned symmetries are reflected in a second axis or not. I recommend you to follow this algorithm to identify each of the 17 groups correctly. After this theoretical introduction, our next stop is the Alhambra. The Alhambra of Granada, built in the 13th century, was declared a World Heritage Site in 1984. Built on the Sabika Hill, this wonder of the world is considered one of the most emblematic works of Muslim art in the world. It exhibits spaces, light, and geometry in an exceptional way. Moorish art, developed by the Arabs in the Iberian Peninsula, took the concept of symmetry to new realms due to their abstract character. Some interpretations within Islam restrict the representation of humans, animals, or any other figurative subjects. These limitations, imposed in the Quran, did not dampen their creativity, but rather fueled their imagination, creating majestic and original geometric patterns. That is why the Alhambra of Granada is of great attraction for mathematicians. Currently, it is the only monument before the 19th century in which at least one example of each planar crystallographic group proposing Fedorov's theorem appears. It is almost impossible to comprehend the genius with which the Nasrid architects operated, designing mathematically intricate patterns of such magnitude, without the knowledge of proven theorems, enshrining these places and their constructors in the annals of mathematical history. To think not just one or two, but all 17 of Fedorov's possibilities are on display. That being said, let's start our visit. We begin our journey through the Access Pavilion, leaving behind us the murmur of the water from the Royal Canal. We walk along the clubstone, passing the Medina located on the right and the 7th-floor gate on the left, and crossing the archaeological area of the Abencerrajes Palace, we access the core of the Alhambra complex. We continue down the Royal Street until we reach the Palace of Charles V. A few meters ahead, we find the first example of a crystallographic group on the front wall of the Wainsgate, corresponding to the crystallographic group PG. By means of sliding symmetries and translation of the minimum region colored in green, we can obtain the mosaic. In the inside vaults of this same doorway, there are also visible remains of some triquets colored in reddish stones, a mosaic with code P31M. The green points denote all the 3 rotations, and the black points indicate the intersection of 3 axes of symmetry, so-called all the 3 points. Before leaving the Wainsgate and still looking up, we see the third and last example located in this space. Its code is PGG, and we will analyze it in a few seconds. Next, we head directly towards the Nasrid palaces. Although we can find different mosaics in various parts of the monumental complex, the richest and most abundant of them are found in the Nasrid palaces, which is why we focus on this space. We will follow the marked route. We enter the palace complex through the messuar, where we will immediately find an example on the entrance floor, in this case of the crystallographic group PGG, the same that we have just seen in the Wainsgate. In the geometrical analysis, we see the centers of rotation of all the 2 in black and the axis of symmetry drawn in red. The fundamental parallelogram is shaded, as well as the minimum region. In each of the examples that we will see throughout this video, these elements will appear in the geometric analysis, in addition to the translation vectors that indicate the direction in which this region must be translated to form each of the mosaics. We enter the messuar and keep walking. The windows of the messuar oratory correspond to group P6. All of them are current reconstructions. Sketch blue, we have a point through which 2 axes of symmetry pass, also called point of order 2. In green of order 3, and in red those of order 6. We change rooms and move on to the golden room. The existing columns on both sides are decorated with tiles containing examples of the group CM. The axis of reflection and sliding reflections that define this crystallographic group are drawn in red, the former in a continuous line and the latter in a dashed line. In the center of the courtyard, the fountain bowl has a marble engraving that corresponds to the PMG crystallographic group. The symmetry axes are shown in red. Finally, before entering the access pavilion to the Court of the Myrtles, we observe another example in the doors of the facade of Comares. The door lattice represents a mosaic with code P4. This mosaic is defined by rotation centers of order 4 and order 2. We cross the facade of Comares and access the corridor that leads to the Court of the Myrtles. Despite its short length, we find some more examples. Now it's time to immerse ourselves in the greenness of the pool. Following the marked route, we turn left, where we can see one of the most famous mosaics, the Nazarite bow ties with code P1. The region to be moved is shaded yellow. Our next stop is the Chamber of the Ambassadors. To get there, we first pass through the room of the ship. The side walls are covered with a black and white tiling corresponding to the plane group CMM. In blue, we find the centers of rotation of all the two, and in red again, the perpendicular axis of symmetry. Not too far away, we discover a mosaic with code P4M in yellow and green colors. In the geometric reconstruction, we see the symmetry axes, which are forming 45 degrees angles. In green, we notice a point of all the two. Remember that this meant that two lines of symmetry pass through it. And in red, a point of all the four. Next, we find these small columns presenting a decoration that we can classify as PM. To construct this mosaic, we reflect the section shaded in brown with respect to the axis drawn in red, and then translate the figure by the distance dictated by the translation vectors. On the adjoining wall, we have again a plasterwork in which blue and green colors are faded. We will catalog it as P1. As we saw with the Nazarite bow ties, which had the same code, we have a minimal region that we are moving to form the whole mosaic. These decorations are repeated in the east wing of the room of the ship, whose name could be inspired by its semi-cylindrical vault ceiling, or from the inscription Al-Baraka in Arabic blessing, written on the plasterwork we have just seen. If we look up, we see some small columns that have the same mosaic that had the fountain of the Golden Room, a PMG code. In the door jumps of the access archway to the next room, we contemplate takas with the design of the so-called Nazarite plane. Its code is again the CMM, with the centers of rotation of all the two in blue and the axis of symmetry in red. We move on to the Chamber of the Ambassadors, also known as the Hall of Comares or the Throne Room. This room is often referred to as the jewel of the Alhambra. In it, we find 9 alcoves that repeat ornamental patterns 2 by 2, adding up to a total of 4 different crystallographic groups. In the first bedchamber, we find another of the best-known mosaics of Muslim art, the Nazarite bones, with code CMM. We realize that this code is quite recurrent in the decorations present in the Alhambra. The second one is decorated with the same design that we mentioned in the room of the ship, this time only in yellow. The columns present in these rooms contain a tiling in green and black tones with code CM. We see the axis of symmetry in red. Alcove number 4 contains tilings on its walls that again it's a CMM. As we have mentioned before, we can see that the other alcoves repeat the design of their opposites. In the walls of alcoves 3, 5 and 7 that we have not mentioned, we find striking rose windows and tapestries that we will leave for another day. We leave the throne room, crossing again the court of the Marals. We access now to the extraordinary Court of the Lions. As Washington Irving said, "I'm prone to seek those parts of the Alhambra which are most favorable to this phantasmagoria of the mind, and none are more so than the Court of the Lions and its surrounding halls. Here the hand of time has fallen the lightest, and the traces of Moorish elegance and splendor exist in almost their original brilliancy." This first sample we found is a key mosaic with a code P4. In green, we see the center of rotation of all the 4. Surrounding the Court of the Lions, we first enter the Hall of the Abencerrajes. If we look to both sides and upwards, we see examples of P4G, one of the most difficult groups to find in the current tour of the Nazareth palaces. In its geometrical analysis, we have the center of rotation of all the four in blue and the axis of symmetry in red. Inside the chamber, we discover an example of PG. Sliding axes of symmetry are indicated in red. Before leaving this magnificent room, we stop at the exit arch and look up again. In this case, we have to sharpen our eyes a little to be able to appreciate the small triangles inside these clusters. This is an example of P3M1. The red lines correspond to the axis of symmetry. Continuing our visit, we now move on to the Hall of the Kings, where we find a great diversity of patterns. On the right, we find the first one. This plasterwork mosaic is identified as a P4. This crystallographic group contains only order 4 and order 2 rotations, as we noted earlier. Right next to it, we have again a CM, same design, although less complex than the one we found in the throne room. In the columns throughout this room, we can see two types of colorful tilings. The first is catalogued as P4M. We can see the axis of symmetry in red, displaying points of order 4 in blue and order 2 in green. Continuing through the Hall of the Kings, we find another plasterwork different from the previous ones. However, it's again a P4. The other tiling present on the columns is also a P4M. Likewise, we see the axis of symmetry in red showing the corresponding points. Immediately after, we contemplate another tiling with noteworthy colors. This mosaic is the first example of PMM that we mentioned. It is defined by two perpendicular axes of symmetry. Before leaving the Hall of the Kings, we will analyze this last plasterwork. In this case, we have a sample of the crystallographic group P6. We see the rotation centers of order 2 in blue. In red, the rotation centers of order 3 and those of order 6 in green. Now we leave this room and continue enjoying the Court of the Lions. Our next stop is the Hall of the Two Sisters. Here, again, we find the small triangles mentioned above. Through this room, we access the Lindaraja balcony. Perhaps its undeniable beauty can make this example lighthouses go unnoticed. It is an example with code CM. The lines of symmetry will pass through the middle of the inverted heart-shaped reliefs. We continue our visit through the so-called Emperor's Chambers and travel a few centuries forward in time. In the context of the adaptation of the Islamic palace to its new Christian uses, a series of rooms were built to connect the Palace of the Lions with the Comares Palace. These rooms are attributed to the time of Charles V, although some researchers have pointed to possible interventions in the time of the Catholic monarchs. The new rooms were organized by means of an internally connected corridor and around an irregular courtyard. It was in one of these rooms that Washington Irving wrote his famous book Tales of the Alhambra. We arrive at the court of the Lindaraja and leave the Nazareth palaces. We now head to the Generalife Palace through its captivating gardens. At the end of the Court of the River, or Court of the Main Canal, we discovered the last example of our visit. This plasterwork represents a mosaic of type PG. In blue are drawn the centers of rotation of all the two. Compiling the examples seen so far, we realize that we are missing one of the 17 crystallographic groups enunciated by Fedorov. It corresponds to the group P3. Currently, we cannot find it inside the monument. However, we know that it was part of it thanks to the rest of the tiling present in the museum. This group is determined by all the 3 rotations. And that concludes our mathematical visit to the Alhambra. I encourage you to rediscover the beauty that the Alhambra beholds with this new perspective. You never know where you might find a crystallographic group in this wonder of the world.
No sé si llamé cielo a esta tierra que piso. Si esto de abajo es el paraíso, ¿qué será la Alhambra, cielo?